Okay, in this video, we're talking about Baronett, Chapter 7, Section C, and we're discussing truth functions, and we're getting into truth tables. So, as a reminder, the truth value of a statement is whether it's true or false, and that either a simple statement can be true or false, or a compound statement can be true or false. That's its truth value. Now, when we talk about a truth function, here's what we mean. When you have a compound statement, which involves simple statements brought together by logical operators, the truth value of the whole compound proposition, whether it's true or false, is determined by, it's a function of the truth values of the simple statements that it's made out of and the logical operators. So truth functionality means the truth value of a compound proposition is a function of the truth values of the component statements and the logical operators. Now, we're gonna look at some schematic diagrams of the truth values of certain logical operators and their truth functionality. And we do that, we're going to use statement variables. And those are going to be lowercase letters. They can stand for any statement, simple or complex. We're just going to use these to illustrate the truth values of the logical operators. And a statement form is a pattern of statement variables and logical operators, meaning it's like a compound statement formed out of these statement variables. You'll see it looks like any other compound statement, except instead of capital letters, it's got lowercase letters, because it's they're variables rather than real statements. So let me show you. This will make more sense. Before we get to that, though, an argument form is just an arrangement of these logical operators, and then truth tables show every possible truth value for compound propositions, and they provide definitions for logical operators in this section. All this is just terminology so far, which probably doesn't make a lot of sense to you, but it will help me explain what we're about to look at. Okay, so let's check out what we have here for negation. What we have is an argument form that gives us a definition for the tilde sign. So here's how this is laid out. If you got any statement, we'll call the statement P. When that statement P is true, then tilde P will be false. When P is false, then tilde P will be true. That's all that this truth table is saying. So for example, let's say that P was statement A. Albany is the capital of New York. Now, if it's true that Albany is the capital of New York, then it's false that Albany is not the capital of New York. And if it's false that Albany is the capital of New York, then it's true that Albany is not the capital of New York. In other words, this is just an illustration for what we're talking about with when P is true, not P is false. And when P is false, not P is true. So this is a truth table definition of the tilde sign. Next, let's look at a truth table definition of conjunction. Now, a conjunction brings together two statements, and so we're going to have a bigger truth table. And this truth table, what it illustrates, each of these truth tables, it illustrates all the possible combinations of the truth values of the simple statements. So you could have P is true and Q is true, P is true and Q is false, P is false, Q is true, and they're both being false. And here's what it's saying. The conjunction sign, that dot, the and, is going to be true when both of the conjuncts are true. In other words, P and Q is true when and only when P is true and Q is true. So when P is true and Q is true, then P and Q, the conjunction, is true. However, in these other three cases, when at least one of them is false, the dot is going to be false. So the truth or falsity of the conjunction is a function of the truth or falsity of the simple statements, the conjuncts, as well as the meaning of the logical operator. And this is the definition of when a conjunction is true. So if it's true that today is Monday and it's raining outside, well, then the conjunction of those statements is true. Both the conjuncts are true. But if one of them is false, today's Thursday, let's say, or it's not raining outside, then the conjunction is false. Next is disjunction. And a disjunction is just an or statement. It's represented by the wedge. So a disjunction is going to be true when and only when at least one of the disjuncts is true. The only time that a disjunction is false is when both of the disjuncts are false. So, if you want to say today is Monday or it's raining outside, then if it's raining outside but today's Thursday, the disjunction is still true because at least one of them is true. Because it just said this or that is true. If they're both true, the or statement is also true. It's only when they're both false that the or statement is false. Now, one point of clarification about disjunctions, okay? In ordinary English language, we sometimes use the word or to mean an exclusive disjunction. So with an exclusive disjunction, at least one of the disjuncts has to be true, but not both of them. They can't both be true. So, for example, if we were to say, today is Monday or today is Wednesday, you're thinking it's an exclusive disjunction. It's one or the other. It can't be both. However, dear friends, listen to me on this. Listen. In logic class, you should always assume, unless you're told otherwise, assume that you are dealing with an inclusive disjunction. With an inclusive disjunction, at least one of the disjuncts has to be true and possibly both. They could both be true. So if I say, look, the bank was robbed either by a Bob Jones student or by a Greenville Tech student, then you know what? It could have been the student was duly enrolled in both institutions. So it was both true that it was robbed by a Greenville Tech student and by a Bob Jones student who were one and the same person. Okay, so assume that disjunctions are inclusive. That's going to be important later on. Next, conditional statements. The horseshoe. All right, this one also gets subtle, all right? A horseshoe, a conditional statement is an if-then statement. If this is true, then that's true. If you drive south on I-15, then you're going to get to Los Angeles. Now, let's look at this truth table here that defines the truth conditions for the horseshoe. If P is true and Q is true, then the horseshoe is true, right? It's true that if you drive on I-15, then you'll get to Los Angeles. But what about this second line of the truth table here? If P is true and Q is false, then it's going to be false that if P then Q. If it's not, if you drive south on I-15 and you don't get to Los Angeles, then it's that if then statement is false. That is the only line of the truth table when a conditional statement of horseshoe is false. When the antecedent is true, but the consequent is false. It's false. Now, look at these last two. These are weird. What if the antecedent P is false, but then the consequent is true? Like you didn't drive south on I-15, but you still got to Los Angeles. Is this conditional statement true or false? It's true because the conditional statement doesn't say you're only going to get to LA if you drive south on I-15. That's not what it says. It says, well, if you do drive south on I-15, you'll get to LA. But if you took some other route, you still get to LA. That's completely consistent with the conditional statement we have here. If you drive south on I-15, you're going to get to Los Angeles. That one can throw you off. You're going to need to study this one and get it in your head right. The same, and then look at this last line. What if P is false and Q is false? The antecedent is false and the consequence false. In that case, the conditional statement, the horseshoe, is true. Why? Because you haven't falsified it. You didn't drive south on I-15 and you didn't get to Los Angeles. Well, that doesn't falsify. If anything, it's consistent with, and in a certain kind of way, it feels like it confirms the conditional statement that if you do drive on I-15, you will get to LA. You didn't falsify it if you didn't drive on I-15, you didn't get there. So that is true under those circumstances. Here's the takeaway point, okay? If the antecedent of a conditional is false, then the conditional is true. I know it feels so weird. It feels so wrong. You need to study it, memorize it until it gets in your head. It's going to throw you off, I promise, if you don't really give it some attention. Next is the biconditional, if and only if. Now, a biconditional, a triple bar, is going to be true when both the antecedent and the conditional, or rather both the statements on both sides of it have the same truth value. They can both be true or they can both be false. The biconditional is going to be true. So, for example, if I were to say, I'm making this up on the spot. You are a gamecock if and only if you are a student at the University of South Carolina. Okay, let's say that's our biconditional. Well, if it's true that you're a gamecock and it's true that you're a student at South Carolina, then that if-then statement is true. But if it's true that you're a gamecock, but you're not a student at South Carolina, well, then obviously the biconditional is false. Oh, you can be one without being the other. On the other hand, if you're not a gamecock, but you are a student at the University of South Carolina, again, I guess that biconditional doesn't hold. You don't have to be both. So that it's false. Now, but if you're not a gamecock and you are not a student at the University of South Carolina, you haven't falsified my claim that you are a gamecock if and only if you are a student at the University of South Carolina. So therefore, the biconditional is true. Bottom line, the triple bar is true when both those statements have the same truth value, whether both true or both false. Okay, let's do an exercise here. Now, if it's true that if R then S, then which of the following is correct? Does R have to be true? No, it doesn't. You want to know why? Look back at this truth table. Are there any times when a conditional statement is true, but the antecedent is false? Well, yeah, look at these bottom two lines of the truth table down here. I told you if the antecedent is false, the conditional could be true. Okay, so A is not right. R could be true or false. If the conditional statement is true, then does R have to be false? No, certainly not. Again, look at the truth table here. Is there any lines? I'm sorry. Is there any lines where the conditional is true, but I lost what I was saying. Where R is true? Well, yeah. Look at this one. The antecedent is true and the conditional is true. So this one's not right. But here's the right answer. R could be true or false with a conditional statement. Now, how do we know the answer here? Because we knew the truth table definition of a horseshoe. You need to learn the truth table definitions of each of the logical operators. and to know when each of those logical operators are going to be true and when they're going to be false. All right, I'm going to take a break here.